as I said, it's difficult to determine that Vmax experimentally. And the reason why is because it's an equation for a hyperbola. We don't like that. We want to make it the equation of a line. So what we're going to do is make it in the form of y equals mx plus b. And what we've done is we've done a reciprocal for each side. So we've turned things over. So the difference between what we have up here and what we have down here is just the inverse. So you can see what we have up here and have down here is just the inverse. And what we've done is then between here and over here is just separated these, the Km plus the S. So here we have the Michaelis constant over what we have in the denominator plus the substrate concentration over the denominator. Well, we know that substrate concentration is going to cancel here. And so here we have 1 over V, 1 over the rate equals y equals mx plus b. We can change that. And you can see that in the next slide. We're going to separate out that 1 over s. This is called a double reciprocal plot, where we're going to plot 1 over the rate versus 1 over the substrate concentration. So really what we're doing is collecting the same data. Collecting the same data as we did for the Michaelis plot, except how many data points do you need to make a line? 2, right? You need 2 data points. How many would we need to get the equation of the hyperbola? A lot, right? So you need at minimum 2. Normally I wouldn't be happy unless I had 4 or 5, right? So that you can really make sure that you have a true line. And so even 4 or 5 experiments is better than probably 20 to make a nice hyperbola. So that is the advantage, fewer experiments. But here we have the equation of the line, and we can get information very easily from this. The y-intercept is going to be 1 over the maximum rate, and the slope is going to be Km over Vmax. So I asked you I let you know that you didn't need to memorize the Michaelis equation, but I do want you to know this Lineweaver-Burke equation. I want you to know that we are going to plot 1 over the rate versus 1 over the substrate concentration. And when you do that, the y-intercept is going to be 1 over Vmax, and the intercept is going to be Km over Vmax. So I'm going to ask you, how are you going to get this information? How would you get Km from a Lineweaver-Burke plot? So here's this is the Michaelis equation in a double reciprocal form. And we can see that when we do the plot, the slope is going to be Km over Vmax, and the y-intercept is 1 over Vmax. So you can solve for Km very easily with the y-intercept and determine what the Vmax is, and then plug that into the slope. We all know algebra, right? It's not that I'm going to give you some data, ask you to plot it, and then determine these things. I'm not going to do that on the exam. But I am going to ask you more detail about this equation and how to get things than I would about the Michaelis equation. Now, how do we use this? Why am I so concerned about this? Well, this plot is used to determine the effect of inhibitors on our enzymes. And this is why we want this plot in the first place.
Can you repeat that, please?
The Lineweaver-Burke plot is used to determine the effect of inhibitors on our, and activators actually, on our enzymes. So by adding another molecule to the mix, we can see what the effect is on binding by just doing the experiments with and without the activator or inhibitor. So again, the Lineweaver-Burke plot helps us look at enzyme inhibitors. Okay, what inhibitors do is they interfere with enzyme action. They may be reversible or irreversible, meaning the irreversible inhibitor is like a permanent poison to the enzyme. We're not going to be talking about irreversible inhibitors. We're going to limit our discussion to reversible inhibitors. That means that it can bind and then dissociate from the enzyme. And the different types of inhibitors that we're going to talk about are just 2. There's more to them than this, but a competitive inhibitor binds, it competes for the active site. It binds to the active site and blocks access. A non-competitive inhibitor will bind somewhere else, but that binding changes the conformation of our enzyme and then affects its ability to make product. We're going to talk more about each one of these. And I just want to, we're taking a very simplistic look at this. If you read more advanced text, they're going to go into more detail about these and maybe different types. So we're just looking at the very surface of types of inhibitors. There's mixed type, there's all different types of inhibitors, but we're going to focus on these two. And our Lineweaver-Burke is going to help us determine the difference between these. What kind of inhibitor do we have? And I'm sure it can give us more information than that, but what we're doing is, in this class, we're just going to look at the difference. So here is our picture for our two different types of inhibitors. So this blue one is a competitive inhibitor. It's going to block the axis of the substrate to the active site. So what do you think about the shape of the inhibitor?
Similar?
Yeah, it's going to be similar. Yeah. And then, the non-competitive inhibitor is going to bind somewhere else, but see how it's going to change the active site shape. Now, this is sort of, my definition of non-competitive inhibitor is not really going to be that, this picture doesn't really show it too well. Here, we're showing that it doesn't bind at all. What I want you to know is that it can bind, but it can't make product. So a non-competitive inhibitor still allows the substrate to come in, but it doesn't allow the enzyme to produce product.
During the normal enzyme catalytic cycle, the substrate encounters an enzyme with a specific active site to which it binds, forming an enzyme-substrate complex. The enzyme then facilitates the breakdown of the substrate to its products, which part from the enzyme, leaving the active site free to catalyze another substrate as the cycle begins again. Competitive inhibition occurs when an enzyme encounters a blocker which mimics the properties of the substrate and binds to the enzyme's active site. Thus, when the substrate is encountered, the active site is not available for attachment and no reaction will occur. Non-competitive enzyme inhibition involves the binding of a blocker to the enzyme away from the active site. This binding causes a conformational change in the enzyme, altering the shape of the active site, which prevents the substrate from binding. No reaction will occur as long as the non-competitive blocker is bound to the enzyme.
Now this is where my difference comes in. Oh, I don't want it. No, away. You never know what's going to come up. In our model, in this, the way I'm teaching it, we can, with a non-competitive inhibitor, we can form that enzyme-substrate complex, but it's just not going to form the product. And again, we're not going to study an irreversible inhibitor. It is a permanent poison on our enzyme, so we're not going to study that. So let's talk about each one of these a little bit more and see what the effect is on our Lineweaver-Burke plot. So again, a competitive inhibitor competes with the substrate, as we saw in that video. So here we compete. So what we're going to do in our thought experiment here is we are going to say we're holding the enzyme concentration constant. So say we have 100 enzymes. And we're going to hold the inhibitor constant. Let's say we have 10 inhibitors. But we can vary our substrate concentration. All right, so let's keep that in our mind. But we can see two things can happen to our enzyme. It can either bind to our substrate or it can bind to our inhibitor, one or the other. And here is our equilibrium constant for the dissociation of that enzyme inhibitor complex. Remember, this is a reversible one, so it can dissociate from it. So again, this is our competitive inhibition. It binds right into our active site. but it can be released. So that's very important. So with no inhibition, we have our y equals mx plus b. Now, what happens is in the presence of our competitive inhibitor, our Vmax doesn't change, but our Km does. All right, let's think about that. Let's imagine that we have our 100 parking spots at Crossgates Mall, and our inhibitor is scary motorcycle drivers. Okay? They're not shopping, they're just coming in there to talk to each other, as you'll often see at rest areas. Do you see them? Like I don't know, they must go to like conventions and travel together. And you're like, oh, do I want to go on that one? No, I don't want to go on that one. Anyway, so they're scary motorcycle drivers. There are inhibitors. Now, we have 100 spaces and 10 inhibitors. And remember, they're all stupid. If you are the first 10 shoppers to come to Crossgates, and those inhibitors are there, do you notice the inhibitors? There's 10. You can still find a spot, but you're going to notice that they're there. They're going to take those nice spots right by the door, right? So you'll notice their presence. You'll have to be shot out of some parking spots. All right, now let's say that there's still only 100 spots and only 10 inhibitors, but now we have 1,000 shoppers. What we're going to do is swamp out those inhibitors. And that's you can use that term in your answer on the exams. So we can swamp them out, meaning that if we throw 1,000 shoppers and 10 inhibitors, are you going to notice the 10 inhibitors? I'm not even going to notice them when I go shopping to notice that they're not going to scare me off from finding a spot, right? You're not going to notice the effect. Does that make sense, guys? So you're competing with an inhibitor for the parking spot, okay? And because it's a reversible one, you're all being thrown in at once, and it comes out and goes in. So that is the case for a competitive inhibitor. The competitive inhibitor is like the motorcycle driver, competing with you for the shopping parking spot, but they're not going to shop, so it doesn't make product. So Vmax, let's think about our plot here. The cars are shoppers. The cars are shoppers. Are you and me? We're going to go shop and make product, right? Don't worry about that. In here, it's substrate. Substrate is, I is inhibitor, substrate is us shopping at Macy's. No, Macy's is at Colony Center, right? Oh, but the good one's at Colony Center. Okay. All right, so I'm going back to the Michaelis-Menten plot. Okay. You guys see this? Everybody know? Can you stand up? This is the Michaelis plot. So what it is, I just want to make sure that I have this on the thing here. So at what kind of substrate concentrations would you measure Vmax? Can you determine Vmax at low substrate concentrations? No, you have to determine Vmax at high substrate concentrations. At what I'm going to call swamp out conditions. So that's why with competitive inhibition, we are not going to change Vmax because we measure Vmax at high substrate concentrations. But Km is measured at low substrate concentrations. It's down here. It's 1/2. low substrate concentrations. So we are going to notice the effect of the inhibitor on Km. So a competitive inhibitor does not change the Vmax, but it does change the Michaelis constant. So what I have down here is low substrate concentration, swamp out conditions. So that's what you need to remember. That a competitive inhibitor, because of my silly little description, which has worked for me for many years, that because it comes in and out, because you're competing, if you swamp it with 1,000 substrates and you only have 10 inhibitors and 100 spots, 1,000 substrates aren't going to notice the 10 inhibitors. But if you have 10 substrates and 10 inhibitors, you're going to notice them. It's going to affect the affinity of the enzyme for the substrate at low concentrations. But it's not going to change at high concentrations because of that swamp out effect. So what is it going to change on our plot? It's going to change, and I don't expect you to remember this equation, all right? It's going to change our Michaelis constant in this fashion, but it's not going to change our Vmax. So our y-intercept stays the same, but our slope changes. So this blue is without inhibitor. When we add inhibitor, we're going to increase the slope. But that y-intercept doesn't change. So you can imagine that I might show you a plot without an inhibitor and with an inhibitor and ask you what kind of inhibitor do we have, and then to explain why do we see this change. And we see this change because we're changing slope, which has the Michaelis constant in it. All right, we're changing slope, but not the y-intercept. The slope changes because the Michaelis constant changes. And it's in that slope term. But the y-intercept doesn't change because the Vmax isn't changing because we can swamp out. So you would need, to see what kind of inhibitor you have, you would need 4 experiments, right? That's not bad. That's not too bad of a job. And there you go, a chapter in your PhD dissertation. Anybody planning on going for their PhD? Yeah. See, I gave you an idea. And why do we care? Well, a lot of our drugs inhibit enzymes, right? A lot of the molecules, maybe some of the poisons in the water that are going around might. In my town, they just discovered some stuff in water, although it's only 9 ppbs above the level. It's this byproduct of the chlorination process, and the level of them is supposed to be 80 ppbs, and it's 89. So I'm not really too worried about it, but Physics Falls is not in the same situation. All right, so again, is there any questions on this? Yes?
Sorry, what is the pink and the green again?
The pink and the green is when you have inhibitor with it. So here we did the experiment without inhibitor. So here we did the experiment where we took different substrate concentrations and we measured the rate. And all we did was plot 1 over so we could get a straight line. And so this experiment is without any inhibitor. What did we get? But when we add the inhibitor, we change the slope in this fashion. All right? Here we did the experiment for the green one. We did the experiment at a couple different substrate concentrations, but kept it the same inhibitor concentration. And then for the next line, the pink line, we doubled that concentration of inhibitor and then did it at a couple different substrate concentrations.
So they're both competitive?
It's the same inhibitor. The I is the same inhibitor. What we did is we just increased the inhibitor concentration.
Would it look the same if it was a non-competitive inhibitor?
No, we're going to go through that next, we're going to talk about what a non-competitive inhibitor does. So the Lineweaver-Burke, the purpose of it, or one purpose of it, is to determine what kind of inhibitor we have. And if you see a change in the slope but no change in y-intercept, you're going to know competitive inhibitor,
Change in slope, no change in.
y-intercept. But I'm going to ask you to explain that.
Right.
I want you to know, okay, the Michaelis constant is in the slope, and the Vmax is in the y-intercept. And that because we can swamp out a competitive inhibitor, and Vmax is measured at high concentrations of substrate, then the Vmax doesn't change. However, the Km is measured at low concentrations, and that's where it does affect the affinity of the enzyme for the substrate. Now we're going to talk about non-competitive inhibitors. I said it was a little bit more complex than what that slide in the video were mentioning. The inhibitor does bind to our enzyme, but it binds in a different spot. So substrate can still bind to it, it just can't make product. So here at the top here, this top one, is what we have normally without the inhibitor. Okay? Enzyme plus our substrate makes our enzyme substrate complex, and then we make our product and have free enzyme. So this is normal without the inhibitor. However, what we can do is if we add the inhibitor, it can bind to either free enzyme or it can bind to the enzyme substrate complex. And by doing that, it stops the enzyme from making product. It doesn't stop it from binding the substrate, but it stops it from making product. So this is why we have a couple equilibria involved. Here we show where the enzyme, the free enzyme, can bind the inhibitor reversibly and make an enzyme inhibitor complex. That can still bind the substrate, it's just not going to do anything. Here we show the equilibria between the enzyme substrate complex and the inhibitor. This substrate may not have, this enzyme may not have made product yet with the substrate. And if the inhibitor binds to it before it makes product, it makes this enzyme substrate inhibitor complex that won't make the product. So it's a little bit more complex, but the idea is that the substrate will still bind, it just will not make product. So what's happening is, and the idea that I want you to think about in terms of our little shopping experience is you're still 100 parking spots, 10 inhibitors, but instead of the inhibitors being our scary motorcycle people that will back out, what we're doing is we're taking, out of the 100, we're putting cones in 10 of them. And those cones can't be removed. Okay? Those cones cannot be removed. So no matter what concentration of substrate we have, 10 are taken out. Can't use them. So instead of 100 spots, we only have 90 spots. So our enzyme isn't going to work as effectively at no matter what concentration we're at if we take 10 parking spots out. So in here, in the competitive, we could swamp it out because we're all competing for the same spots. The Harley guys come out and we can take their spot, right? We're all maybe rushing at once for those spots. If there's only 10 of them, they're not going to affect us very much. Same amount of shopping is going to be done. However, if we show up at the mall and 10 spots are permanently taken out, then the person that is doing the checkout at Old Navy is going to notice fewer shoppers coming in, fewer products being bought or made, right? I know it's weird, but the weirder it is, the better, right? So it's going to change Vmax, but we see Vmax in both. So again, here is our non-competitive inhibitor. It's going to bind somewhere else. The substrate can still bind, but it's not going to make our product. It cannot the substrate, increasing the substrate concentration cannot overcome. We can't swamp out. So because we're changing Vmax in this fashion, it's changing both the slope and the intercept. So this is the kind of effect we have. This minus I is our normal experiment without inhibitor. And then we add the inhibitor, the non-competitive inhibitor, and we see that both the, when we see that the intercept and the slope have changed. And that's because it's changing Vmax. So again, a competitive inhibitor is changing the Km. You'll only see Km in the slope of our Lineweaver-Burke plot. So that's why you'll see a change in the slope when you add inhibitor, but not in the intercept for a competitive inhibitor. For a non-competitive inhibitor, we're changing the Vmax. You see Vmax in both the slope and the intercept, so we're changing both. Yes? Sure, absolutely. So in a competitive inhibitor, we are changing the Km, but not the Vmax. And because we're changing the Km, Km is only present in the slope term of our Lineweaver-Burke plot. So we see a change in only the slope, but not the y-intercept. In a non-competitive inhibitor, we're changing Vmax because we can't swamp it out. We're changing forever the rate at which the enzyme can make product. So you see Vmax in both the slope and the intercept term of the Lineweaver-Burke plot, so you'll see both changing. So the difficult part is not in memorizing what is what. You know, when I show you a plot what kind of inhibitor it is, you can memorize that pretty easily. But I want you to be able to articulate, and you can use my example, or you can use more scientific terms, articulate why that is. And the homework that I put online after this class has a spot for you to articulate that. Yes, Amanda?
The non-competitor inhibitors, the slope is also increasing?
Yeah, for the non-competitive inhibitor, the slope is also changing, yes. Because Vmax, the slope is Km over Vmax, and for the non-competitive inhibitor, we're changing Vmax.
Is it increasing from where they were?
Yeah, when you add it, yeah, it's increasing. I'm just asking basic, it's changing, okay? I mentioned there's other types of inhibition. There's uncompetitive, we're not going to study these, that involves an inhibitor that binds to only the enzyme substrate complex, but not to the free enzyme, and the enzyme is unable to release the substrate as a product. If you increase the substrate, you increase the rate, but never back to the original rate, so the Vmax is going to change. And you see this kind of inhibition when an enzyme binds to more than one substrate. And what happens is you're just shifting the Lineweaver plot, but the slope remains the same. I'm not going to ask you questions about this. I'm just introducing other things to you. I'm not asking questions about this. We're going to limit our discussion to the competitive and non-competitive. I just wanted to tell you that there's other types. And then there's mixed, that the binding of the inhibitor affects the binding of the substrate, but it's more similar to non-competitive.